Hey everyone, my name is Dr. Paul Kerstetter, and today I want to talk about a common question: how fast is my FPGA? Unfortunately, there isn't a single speed number that applies to a given FPGA. The most reliable way to determine how fast an FPGA can run is to develop a model of the design that will live inside it and then perform a timing analysis. The more accurate and detailed your model, the better you can predict whether the FPGA will meet your speed requirements. In this video, I'll start by showing how to determine the flip-flop performance of an FPGA. That is, the maximum rate at which its flip-flops can be clocked. Then I'll insert logic between the flip-flops to demonstrate how adding combinatorial logic reduces the achievable clock speed. For this demonstration, I'll be using the Zynq UltraScale FPGA on the ZCU 104 development board. To better show you what I'll be doing in the video, take a look at this diagram. This diagram is of the Zynq UltraScale FPGA, and all I'll be doing is simulating 3 flip-flops hooked in series. And all the purpose of this is to determine the flip-flop performance. In other words, how fast can we clock these flip-flops in a Zynq UltraScale FPGA? Next, I'll put a logic gate in the path of the flip-flops, and I will show you how that reduces the speed that this design is able to achieve. As for the external logic, all I'll be hooking up to the Zynq UltraScale FPGA are flip-flops, and that's shown in the diagram in these clouds. Okay, so to start off this video, the first thing I'm going to do is I started up Vivado, and I'm going to create a project. And I'm going to go through the create a new Vivado project GUI. Hit next there. Let me set the folders up. Select that folder. Let's call this 3 flip-flops. It's an RTL project. I'll add my sources later. And the targeted device that I'm going to be using is found on the ZCU 104 development board. It's a Zynq UltraScale. Hit finish. Okay, our project is open. Now let's assign or load the VHDL code, and I already have that written. Okay, hit finish. Let's take a look at the code. The code is fairly simple. It's one of the most basic things you can do in VHDL. First off, you have your libraries, some comments. Then you have the entity declaration 3ff_top. And then we have our ports. We have data in, clock, reset, and data out. And those are single wires or signals. Next up is the architecture block. We have 3 signals, D1, D2, D3. And then we have the beginning of the architecture block here. And we have 1 process. And what this process does is set up 3 flip-flops in series. Data in from our input port goes to D1, D1 goes to D2, D2 goes to D3, and then finally D3 goes to the output port, data out. And this process is clocked with a clock and also has reset. If you notice, reset is in this if statement, And because it's in this if statement like this, that means it's an asynchronous reset. It'll happen before the clock or takes priority over the clock signal. So the next thing I want to do is I want to show you the schematic of the VHDL, and to do that, you expand RTL analysis, expand open elaborated design, and then click on schematic, click OK. Let's expand the schematic window, and so there you have it. This is what our VHDL described, 3 flip-flops in series. You have the clock here, and the clock here, and the clock here. And then you have the data going in here, and coming out the queue, and going in here, and coming out here, and going in here, and coming out here. And then you have your reset. So 3 flip-flops. That's exactly what we were expecting. The next thing I want to do is run synthesis, and that will synthesize the design. Okay, the design has been synthesized. Let's expand the open synthesized design. Let's take a look at what the schematic looks like. Let's expand the schematic. And so now the schematic looks a little bit different from the RTL schematic. If you notice, there's a LUT here. There's 3 flip-flops, and they have even more inputs than there were in the RTL design. There's a buffer. This is a buff GCE. This is a global clock buffer, and that puts the clock on the global clock network. And then we have an output buffer going to the output data pin. And these are pins. So the next thing I want to do is establish the constraints. And to do that, I would like to open the window of the I/O ports. And this is the I/O ports where you assign the pins to their physical locations. So here I have a clock pin, and I have this drop-down list, many selections to select from. So the question is, which one do I select? And it's a good idea to select a clock pin, and I'll show you how to tell what a clock pin looks like. You click on the package tab, and let's put all our I/O in this section here. If there's a hexagon-shaped symbol, then that means it's a clock pin, and so you can connect it to that. If you notice there, it says site type IO_L11P. That's the positive side, and L11N is the negative side. In other words, positive or negative, as in terms of 1 versus 0 in logic. And so what I'd like to do is hook it up to this pin, and that says it's pin AJ20, and that says it's a global clock. So I'm going to hook it up to AJ20. There's no, that's not AJ20. There's AJ20. And then for the rest of them, as you can see, it put a little rectangle in the hexagon-shaped symbol. That means that it's been assigned. So next, let's hook up the next 3 signals here into the circles, which are just regular user I/O. Okay, so all I did is I assigned the clock pin to a hexagon-shaped symbol on the positive side, and I assigned the other 3 signals to circular-shaped signals on their positive side. it probably doesn't matter that they're on the positive side. You can also use the negative side as well. But the most important thing now is that you hit the save, and then you name your constraints file. Let's choose a location, put it in under constraints. Constraints. It says it already exists. I'm going to overwrite it. Oh. Constraints 1. It doesn't like me. It doesn't want to overwrite it. Okay, constraints 1 is the name of our file. And if I want to see that I do have a constraints file, you can expand the source file properties or the sources tab, and you can expand constraints. And then you can click on your constraints file, constraints 1, and those are our constraints. Okay, so the next thing I need to do is to launch Constraints Wizard. And Constraints Wizard is under Synthesis, under Open Synthesized Design. Click on Constraints Wizard. So the next thing here is we have our Constraints Wizard GUI. So let's hit Next. And here's our clock. So we're going to set our clock speed to 100 megahertz. It automatically fills in the period of 10 nanoseconds. I'm going to hit Next. So now it wants us to set up our input delays. And this is the constraints that tell us about the circuitry hooked to the FPGA on the pins in the outside world. And the things that we have to come up with are these timing constraints here. And to get those, in our case, we're using a flip-flop. So I need to pick out a flip-flop. Going to DigiKey to pick out a flip-flop. Okay, so this is our menu of options of flip-flops, and if you notice there's one that says clock frequency. So I'm going to choose a flip-flop that is around 300 megahertz. Around that, 275. Let's apply all. Okay, so here is a flip-flop. And we need to look at the data sheet. And now we need to scroll down until we find our timing information. Here's some timing information. So here we have setup and hold. That's not the information we're looking at for right now. Right now we're looking for propagation delay. And if our flip-flop was powered by 1.8 volts, then you can see that our minimum propagation delay, from clock to Q and from clock to Q complement is 0.9 is the minimum, and the maximum is 1.7. So with those numbers in mind, I'm going to fill that into my input delay constraints. So we said 0.9 was the minimum and 1.7 was the maximum. And then for trace delay, our minimum will be 0. And since our clock is running at 100 megahertz, it turns out that 1 nanosecond is 6 inches of trace. So there you go. And so we need to do the same thing with the next, with reset in. Okay, so 0.9, 1.7, 0, 1. Apply. So both of those are filled in, and we go next. So here we have data out, and data out is a little bit different. It wants setup and hold times. So for setup and hold times, I go back to my data sheet, and here's my setup and hold times. We assumed VCC equals 1.8 volts. We have a setup time of 0.7 and a hold time of 0.3. So put that into the constraints editor. 0.7 for setup and 0.3 for hold time, and that's in nanoseconds. And then our trace delay max is 1 and our minimum is 0. Apply, hit next, 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 next. And this would show if we had any asynchronous clock domain crossings. And we don't. Next. Finish. Okay. Now if we reload our constraints file, so there you go. And so we need to do the same thing with the next, with reset in. Okay, so 0.9, 1.7, 0, 1. Apply. So both of those are filled in, and we go next. So here we have data out, and data out is a little bit different. It wants setup and hold times. So for setup and hold times, I go back to my data sheet, and here's my setup and hold times. We assumed VCC equals 1.8 volts. We have a setup time of 0.7 and a hold time of 0.3. So put that into the constraints editor. 0.7 for setup and 0.3 for hold time, and that's in nanoseconds. And then our trace delay max is 1 and our minimum is 0. Apply, hit next, 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 next. And this would show if we had any asynchronous clock domain crossings. And we don't. Next. Finish. Okay. Now if we reload our constraints file, we see we have our input delays and output delays, and we have our create clock, which has a period of 10 nanoseconds, which is 100 megahertz. Let me just expand that screen for you. So these are the sum total of all our constraints. So now we can go back and run synthesis. Okay, next we run implementation. Okay, the implementation is done. Next step is to look at the timing. Here's the design timing summary. And our worst negative slack is 4.444 nanoseconds. In short, everything passes and remember that our clock speed is 100 megahertz. And in our methodology summary, let's run our methodology. Port methodology, let's do that. No violations found. So based on our timing summary, we have a passing design. So our 3 flip-flops will run at 100 megahertz. So let's up the clock speed to, and in order to do that, we have to go to sources and open up our constraints file. And then we have to edit our clock constraint. Let's do a simulation at 500 megahertz and see if it'll pass that. 500 megahertz is 2 nanoseconds. And then we have to change this one too here in our waveform curly brackets. So, okay, so what I did is I changed the period to 2 nanoseconds from 10 nanoseconds, and then I changed from 5 nanoseconds to 1 nanoseconds in the curly brackets. I'm going to save that. Then we're going to run implementation again. Okay, our implementation is done. Okay. So our timing has failed. Our timing has failed. And so let's investigate as to exactly where it failed. It says the number of failing endpoints is 5. Total number of endpoints is 7. It has the worst negative slack at minus 3.360. And then it says total negative slack. That's where it adds them all together, a minus 7.7. So first thing I'm going to do is open the schematic. And then the next thing I'm going to do is expand interclock paths. Going to expand clock. And here we see that we're failing in setup, but we're not failing in hold. There's 2 paths that are failing in setup and 2 paths that are passing. Do you care to guess what paths those are? If you click on path 1, you see that's the output path. So in this case, the flip-flop we chose for the external discrete, external discrete IC, which is a flip-flop, and it's external to the FPGA. In this case, it's failing timing, which means that it won't run at 500 megahertz. But we kind of knew that because when we picked it out from DigiKey, we picked the 300 megahertz part. So we don't really expect it to run at 500 megahertz. So anyway, timing is showing that that timing scenario is failing. The next one is the input, which we get, again, we have that 300 megahertz flip-flop attached to the input of the FPGA, so we don't expect that to pass. And then finally, we have path 3, and the path 3 is passing, and path 4 is also passing, which and those 2 paths are the paths that are in between the flip-flops. So let's go ahead and go back to our constraints wizard or our constraints file, and let's up the clock speed to 1 gigahertz. And to do that, I changed the period from 2 to 1 nanosecond, and I changed that edge there from 1 to 0.5 nanoseconds. Save, and then hit run implementation. Okay, let's look at our timing summary. It looks like our timing got worse when we went up to 1 gigahertz, but we still have 5 endpoints failing and 7 endpoint out of total of 7 endpoints. So if we look at our interclock paths, look at the clock, and as you can see, our paths, the same 2 paths are passing, and the same 2 paths are failing. In other words, the path between the flip-flops is still passing at 1 gigahertz, which is amazingly fast. And then the input paths, the output path and the input paths are failing still. So let's change our clock speed to 2 gigahertz. Okay, this time we have more endpoints failing, 6 out of 7. And if I go to interclock paths, if I go to clock and setup, let's open up the schematic. And it says that path between the flip-flops is failing, but this path isn't. So it's actually, there's a couple of flip-flops here running at 2 gigahertz. Very surprising. But anyway, those two flip-flops must be placed really tight together. But then these two flip-flops, they're placed in such a way that they fail to meet timing. So that gives us a pretty good idea that the flip-flop performance on this FPGA for the UltraScale Plus Zynq device is between 1 to 2 gigahertz. Remember, at 1 gigahertz, we got both flip-flop paths to pass. And so the next step that I would like to do is change the source code. We'll open up the source code. And I want to expand the window. I'll put an AND gate there. And we'll put a okay, so there we put our AND gate in there. And then to show you exactly what I did, let's open up the RTL schematic. Our AND gate. And as you can see, it's in between the path of flip-flop 2 and flip-flop 3. Right there in that path. And so we expect that addition of that gate to slow the timing down. So let's go back to 1 gigahertz and see if our timing passes for our interior signals. Okay, so the timing analysis is done. And as you can see, our output path is failing, our input path is failing. I have the AND gate in here this time. As you can see, it's a LUT there. That's the AND gate. And it's showing that that path is passing at a gigahertz. And that is passing at a gigahertz. I was expecting this to fail, this path to fail at a gigahertz. I did a trial run and I saw that fail before at a gigahertz. But this time it placed it so that it actually passed. So, surprise, surprise. So, based on that, just with that little iteration there, the flip-flop performance for the Zynq UltraScale Plus is about a gigahertz, 1 to 2 gigahertz. But that's not the whole story. The whole story is, you know, how fast your FPGA, really what that depends on is your design. And if you think you're going to be using things like counters in your design or SerDes or FIFOs or whatever you think you're going to be using in your design, you might want to put that into your model to determine how fast your FPGA is. In this case, we only looked at 3 flip-flops and then we put an AND gate in there. And we found that the performance was 1 to 2 gigahertz. But we also found that our flip-flops to our exterior world, there are flip-flops outside the FPGA, which we chose to be 300 megahertz, limited our design, you know, below 500 megahertz. And that was shown in our failure of those 2 timing paths. So it's what goes on inside the FPGA is not the whole story. A big part of it is what's interfaced to the FPGA. And the moral of the story is, the more detailed your model for your design is, the more likely you'll get a more accurate idea of how fast your FPGA is. So that's all for now. I hope you liked this video. If you liked it, please like it and subscribe to the channel. Stay safe, and I'll see you in the next video.